All right, so there were 4 properties that are used to define a gas, and they will show up throughout our gas laws. They're temperature, pressure, volume, and number of moles. Make sure you know the symbols that are used for them. The more common units, temperature, it's not a matter of being common. The only unit for temperature in gas laws is Kelvin, so you have to get used to that. And you might need to be reminded of the formula. So Kelvin, if you're solving for Kelvin temperature, it equals Celsius temperature plus 273. All right, so that'll be real important in this unit. Pressure, it's usually atmospheres, not always. Volume, usually liters, not always. This is an equivalency. You'll get familiar with this unit, 22.4 liters in 1 mole at standard temperature and pressure. What that tells you is that every gas, if it's at standard temperature and pressure, and we just learned standard pressure is 1 atmosphere, standard temperature is 0 degrees Celsius, which is the same thing as 273 Kelvin. So if a gas is under these standard conditions, it will occupy 22.4 liters volume. That is any gas, every gas, regardless of its identity. The symbol for moles is little n. So here we go with gas laws. We're going to start with what is called Boyle's Law. Some memorization that you need to know here, so it'd be a good idea to jot a couple notes down, print out the PowerPoint, or make some note cards. Boyle's Law looks like this, and it basically tells us that pressure and volume of a gas are inversely proportional. What does that mean? That means as pressure goes up, volume goes down. So I want you to think about holding a balloon in your hands. And as you squeeze the outside of that balloon, as you apply pressure, the volume of that balloon will go down. So that's what Boyle's Law says. One of the everyday applications of Boyle's Law is when we actually breathe. I think this is so cool. So you actually don't, breathing is involuntary. So you don't actually consciously or unconsciously tell your lungs to fill up and release air. What happens when your body decides you need to breathe is a little membrane called the diaphragm moves, and that causes your lungs to increase in volume. Look at Boyle's Law. What happens when you increase in volume? They're inversely proportional. So when you increase your lungs in volume, pressure decreases. So you have this huge lung situation with the pressure has gone way down because you've increased your volume of your lungs. And what happens when pressure goes down? You create a little vacuum inside your lungs, and that little vacuum sucks air in to fill it up. And so breathing is really involuntary. Now, when your body feels that it has inhaled enough air, that little diaphragm will move back up, and that will cause the volume of your lungs now to go back down or decrease. Now that you have smaller lung volume, you have caused the pressure inside your lungs to increase, and that forces air to be expelled or exhaled. So let's move to an example. Oop, not an example yet. Okay, here's just a molecular interpretation of Boyle's Law. This kind of may be easier to visualize for you. So if you have a closed container with a gas inside of it and a piston, and you push down on that piston, what have you done to the volume? You have made the volume go down. Therefore, what has happened to the pressure of the gas inside the container? Pressure has gone up. Do you remember what pressure is? Pressure is simply the frequency of collisions of the gas molecules against the container that it's in. If you make a smaller volume, you're going to have a lot more collisions and therefore higher pressure. All right, now if you were to graph, this is typically another multiple choice question you'll see. If you were to graph volume versus pressure, you'll see an inverse relationship, and anytime you plot an inverse relationship, you're going to see a downward curving line. And that's the case with Boyle's law. But in general, obviously, as pressure goes up, volume will go down. All right, this is just another cool example. Okay, so this might be, for example, an extra credit little essay question on your test. How is Boyle's law related to deep sea divers, scuba divers? Well, it turns out, I'm sure you know this, that as you dive down in the ocean, the pressure goes way up, okay? So your body, lungs, every part of your body experiences higher pressure. Remember that atmospheric pressure is 1, and if you get down, let's say about 20 meters deep, your body is experiencing 3 atmospheres of pressure, which is a tremendous amount. And so what's going to happen to your poor lungs at that high pressure? The volume of your lungs is going to go down, and you're going to have a hard time breathing, aren't you? Obviously, divers have breathing apparatus to help with that. One of the biggest dangers for divers, though, is when they start to resurface. And if they do it too quickly, I want you to think of Boyle's law. As you go up, the pressure will be going down. Okay? Pressure goes down, down, down as you get closer to the surface. What's going to happen to your lungs as you surface and the pressure decreases? Your lungs will get larger. Okay? The volume goes up. Okay? And that's actually dangerous, because if you surface too quickly and the volume of your lungs expands too quickly, you can actually burst a lung, and that can be very, very dangerous. So divers have to, as you've probably heard, have to control their ascent very carefully. So I kind of explained all this to you already, but here it's kind of in writing if you want it, especially since I said it might be a multiple choice question. Okay, and again, I'll just give you a minute to read this. Okay, so the solution to that, and in addition to going very slowly from the depths of the ocean to the surface, is to always exhale when you are rising. If you're diving down, when you're coming up, exhale. Do not hold your breath. All right, so here's an example of a calculation using Boyle's law. Let's say you have 20.5 liters of nitrogen gas. You won't need it in this question, but just to remind you, nitrogen is one of the 7 diatomics, and they've given you the temperature and the pressure. And what have we changed here? We have changed the pressure, and it's now asking what's the new volume. So once you read through the entire question carefully, you can see that it is Boyle's law you will need, because Boyle's law allows you to predict a new pressure and volume from an original pressure and volume. Be careful with units. Okay, I'm trying to trick you here. I give you 2 different pressure units. And remember that units in gas laws for temperature always have to be Kelvin. If you'd like to try it yourself, give it a swing. If not, I'll show you how to work it on the next slide. All right, Boyle's law. I'm first going to convert pressure units so that they're all the same. So 740 torr I want to convert to atmospheres, so I know the conversion factor between torr and atmosphere. There are 760 torrs in 1 atmosphere. The original volume, V1, it was 20.5 liters. The new pressure is 9.8 atmosphere, and I'm trying to solve for the new volume, V2. When I rearrange and plug in the math, I get that the new volume is 2 liters. And that's exactly what I expect. I increased pressure, and if you go back and read the problem, I increased the pressure by a factor of 10. Boyle's law tells us if we increase pressure, we expect to decrease, volume. That should say volume. Okay? The second law we're going to talk about today is Charles' law. And whereas Boyle's law related volume and pressure, Charles' law relates volume and temperature. It turns out that volume and temperature are directly proportional, just the opposite of Boyle's law. So as temperature goes up of a gas, its volume will also go up. It makes sense, right? If you heat a gas up, you expect it to expand. So you do expect volume to go up. So this is the mathematical equation of Charles' law. If you are to graph Charles' law, because they are directly proportional, there's no downward curving line, it is a linear relationship. Now each gas has its own precise linear relationship, but what's very interesting is when scientists were studying all the different gases, they realized that the intersection of volume and temperature for all gases was the same. So if you look at the intersection, it would be when is the volume of a gas equal to 0? Now that's impossible, but theoretically what scientists did is they extrapolated these linear relationships they were getting until the volume was 0. And it turns out that all gases, when they're presumed to have 0 volume, it occurred at an unusual temperature, and that temperature in Celsius was minus 273 degrees Celsius. That's where the concept of Kelvin came. So scientists called that absolute zero and developed a new temperature scale called Kelvin, and the point at which all gases reached 0 volume was defined as absolute zero or 0 Kelvin. Charles' law, practical application. This is actually a kind of a fun demo to do. But if you were to blow up a balloon, put it in ice water, and it shrinks. And that's because of Charles' law. So remember Charles' law said that, excuse me, that volume and temperature are directly related. So equals some constant. So as volume, so let's do it this way. As temperature goes down, volume would also have to go down in order to remain constant. This ratio always remains constant. On the other hand, if you put a balloon in boiling water with a higher temperature, the balloon will expand, again demonstrating Charles' law. Oh, hot air balloon, my very favorite. I actually used to, for a while, worked on my pilot's license to be a hot air balloon pilot. So, but anyway, that works on the same principle. It creates a big plume of fire to heat up the gas inside of the hot air balloon, and the balloon expands, and that carries it up into the atmosphere. So it's pretty cool. Oh yeah, this is even more cool. If you ever get dry ice or liquid nitrogen and you put a balloon in it, the balloon just turns into a crinkly mass. So that's a real fun one to do too. All right, so here's an example of a calculation using Charles' law. When you get these sample problems, you're not going to be told, use Charles' law, use Boyle's law. You're going to have to figure out which law is appropriate. So you're going to have to get in the habit of reading them carefully. So I would start kind of circling what the variables are. So in this one, it's talking about volume. And anytime it says a variable is held constant, you can ignore it. So that's just extra words. So let's just get that out of there. It's talking about volume, and it's talking about temperature. So what law do you know that relates temperature and volume? Well, that would be Charles' law. And all of these laws are written in such a way that allow you to calculate a new volume, new temperature from original volume and temperatures. So try to work it out on your own if you want, or go to the next page and see me work it out. Oh boy, I really darked out. Let me rewrite Charles' law. Alrighty, so the original volume was 247 milliliters. Temperature, remember, for gas laws always has to be in Kelvin, so I had to convert that. And we're trying to solve for the new volume and the new temperature in Kelvin. And when we rearrange and solve for V2, we see that the new volume is 311 milliliters. Always ask yourself with these if that fits with common sense. What did we do? We took our original volume, which was less, and we heated it up. What do you expect to happen to the volume when you heat it up? You expect the volume to go up, and it did in fact, so that's good. All right, another law is called Avogadro's law. It's kind of got a lot of words here, so I'm going to try to underline the important parts. The bottom line is equal volumes of gases contain the same number of particles. Okay? Doesn't matter what the gas is. If you have a certain volume, so if I have 1 liter of a gas, it will always have the same number of particles as any other 1 liter of gas. So that's kind of cool. Okay? That's assuming you weren't messing with the temperatures like, with the variables like temperature and pressure and stuff. So, for example, you're going to start getting more and more familiar with the constant 22.4 liters. That particular volume of any gas contains exactly 1 mole of particles. So that can be used as a conversion factor. It's 22.4 liters is 1 mole of any gas. This relationship is not true with liquids and solids, okay? Equal volumes of liquids and solids contain vastly different number of particles, and that's because the packing density of liquids and solids varies a lot. Gas particles are always far apart because they don't have those intermolecular attractions. If you were to plot Avogadro's law, just like any direct correlation or direct relationship, you're going to see a linear relationship. Okay, so straight line here. And basically that's showing you that as the moles of a gas increase, the volume also increases. One final, there are kind of 3 laws that we think of as going together. And that would be Boyle's law, Charles' law, and the Gay-Lussac Law, this one. Okay? Those are all the laws that relate pressure, temperature, and volume to one another. So the Gay-Lussac Law relates pressure and temperature. Pressure and temperature are directly related, just kind of like we saw with Charles' law. And so that means that as temperature goes up, we would expect pressure to go up. So that makes sense, right? Remember what happens to the molecules of a gas when you increase temperature? They start moving around and colliding more. So you would expect the pressure to go up. So that makes total sense. So here's an example of Gay-Lussac law. Let's imagine you have a deodorant can. And so it's a spray deodorant can. I know nobody uses those anymore, like an aerosol can. So it's a metal can that's rigid. It has a set volume, okay, constant volume because it's metal. You know you're not going to change the volume. So you can kind of ignore. Remember I said if something's held constant, you can ignore it. So they're giving you an original pressure and an original temperature. And they're saying what would happen if you put that aerosol can in, let's say, boiling water. So we're talking about pressure and temperature. That is Gay-Lussac's law. So half the difficulty is deciding what formula you want to use to solve the problem. The actual solving the problem is not tough at all. Okay, so I really should have, I just told you that volume was kept constant, and so I am going to, I'll explain what I did in a bit, but for now I'm going to get rid of the volume terms because we know it's a rigid container, volume is constant, and so we're just going to look at the Gay-Lussac part of this law. Volume is constant, so again I'm going to ignore the volume term. And temperature has to be in Kelvin, so we converted them all to Celsius by adding 273. And that tells us that if you have a container of any type of aerosol that's normally at 1 atmosphere, no extra pressure, and you heat it up, let's say even in boiling water, pressure inside that can goes to almost 5 atmosphere, which is really high. So this explains why it's so dangerous to take any aerosol can and throw it in a fire, which some ignorant people have done before, because it will blow up like a bomb and be extremely dangerous. And that's because the pressure inside that can is going up extremely high. So I will, in just a moment, talk about why I even had the volume in here when it was constant. All right, so I have had several students that really find it difficult to keep straight which is Boyle's law, which is Charles, which is Gay-Lussac's, how do they look, what do we do? There's something called the combined gas law. So if you look down here at the bottom of the slide, that has all 3 variables, pressure, volume, temperature. And if you only remember one law, it is the combined gas law, because I'm going to show you how to use this wonderful law to derive Boyle's, Charles, and Gay-Lussac. So let's say, for example, the problem that we just worked, the volume is constant, doesn't change. That would mean that you would get rid of the volume term because it's held constant. And then what are you left with? You are then left with Gay-Lussac's law. Let's imagine now that instead of volume being held constant, that pressure is being held constant. Let's say whatever we're doing is open to atmospheric pressure, and it doesn't change. And so we're going to get rid of the pressure term. And what do we have left now? Whose law is that? That is Charles' law, volume over temperature. And finally, let's say that we hold temperature constant. Temperature doesn't change. So we're going to cross out the temperature term in the combined gas law. Whose law are we left with now? Boyle's law. And so again, if you just memorize the combined gas law, you can use it for any